If those who've joined us, good morning to everyone, are wondering why we are quiet, because we will be starting exactly at 12, so we're just gathering attendees. Hello everyone, and welcome to the 2022 edition of the Peter Wells Memorial Lecture on behalf of the Joint Biomedical Engineering Steering Group. I'll say a few words about this organizing entity before introducing our speaker. The principle of today's webinar is that we will collect questions in the webinar tool that you all have in front of you. Please post your question in there, and I will collect them, and there will be a session for our speaker to answer your question at the end. The Biomedical Engineering Steering Group I mentioned a second ago was initially set up some years back by IPEM and the Biomedical divisions of IET and IMechE to coordinate efforts in the biomedical engineering space. And more recently, this has been broadened to include the Institute of Physics, the Institute of Materials Mining, the Faculty of Clinical Informatics, and the Biomedical Engineering Association. One of the activities of this joint steering group is to every year organize this lecture in a memory of Professor Peter Wells, CBE, who sadly passed away a few years ago. Today, I've got the pleasure of introducing our speaker, Professor Anthony Fisher, who's a consultant clinical scientist in medical physics and clinical engineering at the Liverpool University Hospital, and is also a professor of physics at the University of Liverpool. Initially, Tony graduated in medicine before developing his career towards healthcare science, specializing in physical science. At the onset of the pandemic, he was seconded to NHS England's chief scientist's COVID pandemic response program to contribute to the to contribute the clinical engineering support to this workforce. And today he's going to talk to us about his work, in particular in managing the airborne transmission of the virus. Tony, over to you.
Thank you very much, and thank you, colleagues, for this kind invitation to speak to you today. Jess Shearing-Sylvan introduced me as somebody who graduated first in medicine. Well, that was such a long time ago. I spent almost 40 years subsequent to graduating medicine looking at engineering and physics problems. So recently I've been very comfortable with things like flow of electricity and kinetics and thermodynamics and things like that. But on my journey of 24 months since we joined the pandemic response program, I've had to get used to things like Micrococcus luteus and gram-negative infections and extraordinary things like that. And trust me, for an engineer and a physicist, that's really been quite a challenge. So my talk today is going to be very informal. It's going to be a story, and it's really going to be how engineering and physics has contributed to how we can successfully, I would say, mitigate the hazards that give us the risks associated with the airborne transmission of pathogens in general, but of course, with our recent history, specifically the SARS-CoV-2 virus, which is behind the COVID-19 pandemic. So it's great pleasure that I introduce you to the rest of the team I've worked with. I've got my NHS colleagues who are all clinical scientists, consultant clinical scientists in the NHS who've driven this work forward clinically pretty much. A friend and colleague, Frank Mills, a fellow of IMechE, the chair of the healthcare group of CIBSE, the Chartered Institute of Building Services Engineering. Nick Rhodes, my longtime academic colleague, who's working with me in the validation and verification laboratory in Liverpool, and I'll talk about that later. And two new colleagues, Fred Mondonga and Pawan Gilbert, who provided so much tremendous expertise in our CFD, our computational fluid dynamic modeling, which I'll be talking a fair bit about later on. And their work is supported by, or was at the time, supported by UK research and innovation grants. And then lastly, but no means least, Gary Hognan and his team out at Feedwater Labs, who's contributed so much in terms of practical microbiology and helping me understand what microbiology is all about. Okay, well, so the day's presentation, I'll do a background on what I think the COVID-19 challenge is from how I see it anyway, as an engineer and as a physicist, and then just tell you a little bit about how ultraviolet in the C region of the spectrum can cause bacterial deaths and can deactivate viruses. And some people now call that germicidal UVC. We'll look at how we use that in engineering application, in mitigation devices, and then we'll look at CFD modeling to see what that can tell us. CFD modeling is going to help us bridge really verification and validation exercises. In device verification, are the physics and engineering as per the spec? What the manufacturer of a device says, well, does it deliver that specification? Now that's different from validation, biovalidation. Does it actually kill bacteria? Does this device actually deactivate viruses as per the claim? So we look at verification and biovalidation as interdependent, but in terms of delivery, they are orthogonal, aren't they? And I'm going to end with a few comments on what best practice might be of using this type of technology in the healthcare space, maybe some recommendations, and maybe a tilt towards where we'll be with regulation in the future. So the case studies I was originally asked to look at were based on endoscopy and dental theatres and surgeries. Now the common feature here that these procedures produce large airborne particles called, they're larger than aerosols, but they're called AGPs, aerosol generated particles. We'll look at their particle size distribution in a moment. So this lady is getting an upper GIT endoscope passed down her esophagus. Okay, and this is pretty much what a typical theatre looks like, and it's very, very busy. So it's a complicated space to maintain, logistically, lots of challenges. In terms of ventilation, very difficult. There's lots of nooks and crannies and potential dead spaces. Well, we all know about dentistry, don't we? Here's some poor soul receiving some dental treatment. A typical dental suite in the high street, a chair, some equipment, some dead spaces under desks, possibly some windows which open, maybe they don't. Okay, so there's two scenarios to consider, and I want to look pretty much at just endoscopy and dental surgery just for the moment, and my tilt is towards C19. Okay, so two scenarios. The patient's in the room, the patient is receiving treatment. If that patient is positive, there is a risk to the clinical staff, so we must consider the UK HSE perspective. The mitigation, continuous low intensity air sanitization. Continuous low intensity air sanitization. It needs to be smart, it needs to be unobtrusive, it needs to be sufficiently effective. And we'll look at effective later. The second scenario, the patient leaves the room, assume the room airspace is contaminated. The cleaning staff coming along are now at risk. The next patient coming in as at risk. Fallow time is the mitigation, i.e. the time in between one patient leaving and the next patient arriving. What do we want? Spontaneous clearance? Well, that's probably not enough. Spontaneous clearance does not require, not give us the levels of sanitizations that are necessary. Okay, so it's logistically inefficient. Now, a fallow time is an arbitrary time that the clinical director of a practice will say is the minimum time in between procedures. One might say in an endoscopy suite, normal flow of patients might be 4 an hour, there might be 5 minutes in between patients. But the fallow time needed when there's the risk, the hazard around of SARS-CoV-2, the risk associated with that, fallow times are much increased, but they are increased arbitrarily. And I've heard of 15 minutes to 2 hours being quoted with no real justification why one time is better than another. We might as well go for high intensity air sanitization, make it robust, make it windy, make it agricultural, because there's no patients there to be disturbed. Okay, so the main challenge in endoscopy and dental theatre surgeries are these aerosol generating procedures. That's certainly where we were until quite recently. Maybe the emphasis changed a little bit, but I'm proceeding on the basis that when we started this work, AGPs was a very big focus. Well, the virus that we're considering here is about 100 nanometers in its maximum dimension. Particles that are excreted on the exhaled breath, the respiratory fraction, is from about 100 nanometers up to 5 microns, and they're typically called aerosols. The next size up in the spectrum are these AGPs, 5 to 25 microns, called microdroplets, and in dentistry, there are small spit particles, and they might be up to 0.5 millimeter or something like that. Interestingly, on the physics here, we might say, for practical terms, so it is engineering rather than physics, respiratory particles are so small that they have negligible mass and tend to move around in air currents in the room as they would if they were molecular dimensions. Whereas when we get up to AGPs and beyond, larger particles, they have significant mass, and in engineering terms, we can start to look at these particles having inertia, then momentum, and then precipitating, potentially spontaneous, under the influence of gravity as per Stokes' law. So there's quite a spectrum there between 0.1 to 500 micrometers. Now you might say, well, we can clean the air quite easily and quickly by using HEPA filters. They're very good, they've been around for a long time, and they'll mechanically exclude particles bigger than 25 micrometers, and by absorption mechanisms will go much, much smaller. But in our practice, we've been rather cool on using HEPA filters because there are some issues with them. One being they do clog up and they do require changing. If in a COVID-19 world, they would have to be seen as a biohazard. Things are changing. I think the application of HEPA has got a big future, but certainly when we started on this journey, we decided to exclude HEPA and direct all our efforts towards UVC, germicidal ultraviolet. The principal mitigation for dirty air is changing it. The principal mitigation is the number of ACH, air changes per hour, you can achieve. Okay, well, the simple dilution conventionally will by using the hospital's heating, ventilation and air conditioning unit, and it falls off simple dilution, first order exponential equation for a well-mixed reactive room. 63% new air appears after one change of air, 95 for 2, 99.5 for 4. So it's a first order exponential decay of contaminant, pathogen floating around in the room. Now I'm going to use this expression for a well-mixed room rather often, but you'll see where that goes as we proceed. Okay, so it's easy enough to talk about clearance. That's just the fractional clearance, the fractional change in concentration of a particular pathogen as a percentage. But the infection and prevention control, medics and nurses, favor something called the log reduction. And the log reduction is just a log change in concentration. So a 1 log reduction is equivalent to 90%, 2 log reductions, 99%, etc. A pivotal point at looking at the efficacy of a sanitization process in infection prevention control world is the 3 log reduction metric. Okay, and that would take 10 ACHs after 1 hour, or in terms that we understand as physical scientists, 1 in 10 to the 3, 1 in 1,000, 99%. So that after a 3 log reduction process, only 0.1% of the contaminant pathogen is still floating around in the air. Graphically, these are the exponential curves. We know I put these 4 traces here for what it looks like after 30 minutes, and brought to your attention 1 ACH is 63.2%, the time constant of exponential decay achieved after 1 hour. Okay, this is an example of a portable ultraviolet air sanitization device from the company, UK company Mansfield Pollard. It is, like many of these devices, a box, a fan, an ultraviolet source. The fan either sucks or blows air from the environment across the ultraviolet tubes. The ultraviolet irradiates the passing air and kills bacteria and deactivates viruses. Well, that's the principle anyway. And this device here rolled out in quite large numbers at the beginning of the pandemic. Attractive part of it, 1, it was available, and 2, it's a robust unit that moves very happily around on wheels. This is an example of an environment, critical care environment, whose ventilation has been augmented by one of these devices placed between every other bed. Okay. The effective air changes per hour are those air changes you get from the hospitals, heating, ventilation, air conditioning, plus that provided by the air scrubber, by this portable germicidal UVC device, assuming good mixing. Assuming good mixing, we get exponential decay, exponential dilution. Another device, there's one of these on the wall of One Birdcage Walk. You can look at it next time you're visiting the institution. It's again, a different orientation, but it's a pushing fan which takes air from the bottom, drives it through a chamber. The chamber is lined with aluminium, which is highly reflective to ultraviolet light in the wavelengths of our interest, about 254, something like that, and expels it from the top. This is a wall-mounted unit. The wattage, typically these devices, I don't know, 20 watts or something like that. The fan, 100 watts or something. They're very, very low consumers of electrical power. Okay, this is a device from Philips, a portable unit on the left. On the right, a unit that bolts on the ceiling. Now, stepping up, those are portable units. Now, we've increased our scope of our studies in Liverpool here for the Chief Scientific Officer. into units, large units, that 20, 30,000 cubic meters per hour, that will fit into ceiling ducts. And this example here is one that we're starting to look at now, and it's from Elta fans. Okay, there's a fan there perched on a table, and it's going to blow through this unit here, which is lined with high-power ultraviolet mercury tubes. This is the view from one end, looking into the chamber, again lined with aluminium, not stainless steel, aluminium, which is highly reflective of UVC light. And the engineering is very good on this. And as ultraviolet light, misused, is very hazardous and very dangerous, they've put some very nice interlocks here to detect various fail phenomena, that if they do fail, the ultraviolet light cuts out. And I think this is the very minimum we expect from good engineering here, using potentially dangerous UVC. Okay, this is something my colleague Frank Mills, working with a company called Midtherm. They've put one of these units in the ceiling of a rapid assessment unit down in Maidstone Hospital. And I've just taken this slide from him, and it explains how it works. But basically, this is plopped straight in series into existing ductwork. An attraction of using ultraviolet light like this way is that if it were as simple as the air coming in dirty one end and going out the other, there's the potential to recirculate the cleaned air. Now that sounds quite novel in the UK, but it's not novel in many places throughout the world. For example, in North America, many of the hospitals there use this type of technology and recirculate up to 80% of the air. So that's got, okay, it's very useful for infection prevention control, but potentially, how powerful is that when we look towards optimizing our carbon economy? Simply, we save 80% of our energy. At the moment, the easy way of ventilating your hospital space is you bring in your air from the outside, you heat it, you use it, and you throw it out a window. So that's very inefficient. Things must change, and we think this type of technology has got great future in tackling the carbon issues that we're faced with. Okay, so what does ultraviolet light do to these microbes and these viruses? Well, on the left is the, from an A-level physics textbook, it's the electromagnetic spectrum that we know. It shows the visible bit, the ultraviolet bit on the shorter wavelength side we can't see, and there's UV, A, B, C, and ultra short UV. UVC, okay, is that which is bactericidal and virus deactivating. And mercury tubes that we tend to use peak, or can be filtered to peak, at 254 nanometers. On the right-hand side, we have a depiction of DNA, okay, twin spiral DNA, the molecule of life. That's where our genes come from that make up our chromosomes. Okay, every so often in a DNA molecule, there will be submolecules called thymine. Okay, they're the bases. If two closely related, physically related thymine bases are simultaneously hit by sufficient UVC energy, they spontaneously will bond into a dimer. Dimerized thymine DNA is no longer patentable. Okay, well, it might repair, but generally you might say this is a way of deactivating DNA. And I've shown this in the diagram here. On the left, look at those two yellow bases, which are thymine. Treat with ultraviolet light. On the right, they join together and break the yellow to green bonds on the right-hand side of the twin molecule. Now, DNA is twin-stranded. The viruses, by and large, are single-stranded. SARS-CoV-2 is no exception, and that's RNA. So RNA doesn't have thymine, it has uracil, a similar base, okay, but it is equally or more susceptible to ultraviolet light in the same way. So ultraviolet light at sufficient dose will dimerize uracil in RNA, rendering the virus inactive or deactivated. Okay, right, so we did a simple design study here. Okay, for a given clearance, how can the fallow time, the time in between patients, be reduced from 30 minutes to 10 minutes? So important. Think of endoscopy, which is on for many people the cancer pathway. We really cannot afford in clinical deliverance to slow down the rate of patients through this pathway. So minimizing safely the fallow time is a big challenge. So I won't go through the detail here, but basically we're going to say that we have an existing 5 air changes per hour from the hospital system, and the given system requires 30 minutes because clinical decisions have been made that that's about right, and that we know is going to deliver some sort of clearance. People won't know unless they calculate it. We can calculate it. And what we're saying, that you could import into that environment a portable air scrubber, which would give you additional air changes to achieve that clearance, but in a much shorter time. So for a well-mixed room, the total air changes per hour are the existing air changes plus those which come from the air scrubber. Okay, and we provided a simple tool on the web that people can make these calculations, and it's very, and it's this has been downloaded some 2,000 times or some, or used some 2,000 times. So we've got some sort of traction. And in one little study, the fallow period was required to reduce from 30 minutes to 10 minutes. The clearance improved from 92 to 98% without design, it just did. Caution, this assumed a simple air mixing model. So in this particular scenario, where they were getting a clearance of 92% using the hospital's HVAC system, by adding an air scrubber that's available, it happened to be the Mansfield Pollard device I've already shown you, they could get away with a 10-minute fallow time as opposed to 30. And the bonus, the clearance went from 92% to 98%. Okay, well, to reiterate that slide, look, that's the critical care ward with the single air scrubber in it. And I've highlighted there, assuming good mixing. So air changes per hour provide mitigation. Do they? Is that not a little simplistic? We need to think about the physics and engineering a bit more, don't we? ACHs, how are they deployed exactly? Well, in the displacement of a pathogen suspended in a space, there's a spectrum of mechanisms by which it can be removed. It can be diluted by good mixing, which we've discussed already, or it could, in theory, be displaced with no mixing, a sort of invisible piston flowing across the room with a front of clean air following bad air. Well, there's a whole spectrum of bits and pieces and different mechanisms between that, but we should understand that really, so we know about hot spots and we know about cold spots. Airborne pathogens arise from particular sources. We should know how these sources are distributed so we can optimize the airflow to get these sources maximally diluted. Patently, this is a role for computational fluid dynamics, and we put quite a bit of effort into looking at various scenarios, recently in schools, but predominantly in healthcare spaces. And I'll give you a quick tour now. So this is a model that we set up with Pete Bill, consultant clinical scientist at Birmingham Children's Hospital. So to march you through the slide here, we've got a photograph top right-hand corner. That's what the dental theatre looks like. On the left-hand side of that, we've got a CAD diagram of a treatment couch and the equipment and a couple of people. The main graphic in green there has got that CAD-CAM model showing the air coming from a duct in the ceiling and exhausting to one side of the room back through the ceiling. So already we see that is not the smartest way of ventilating a room. Okay, on the left-hand side, we have two grills. One, the grill on the right is the standard input diffuser duct, and the one on the left is a theoretical one where we took out the middle of the one on the right. This animation shows the deployment of air through that input duct. So on the left, This is the deployment of air from the standard diffuser. And on the same time scale, on the right, is the deployment of air with that diffuser modified simply by taking out the middle section to give a downward jet. And that downward jet goes straight into the clinical area and removes particles generated by the dental procedure by jetting air onto the patient's face. Very simple. Okay. So going back to the original one now, where we don't modify the jet. What happens if we augment that sanitization flow by adding, there we are in the red circle, an air scrubber. Okay. So that's the same heating and ventilation, the air conditioning flow in both cases, but on the right, we've added a portable air scrubber. You can see that the scavenging of air is much, much quicker, much, much more efficient by the simple addition of the air scrubber. So that's telling us something about how air from ventilation systems move around our healthcare space. Okay. Now we have to look at the sources that might come from a patient. Now here's a patient in dental treatment, and this excellent work here is from Fred and Pawan at ES Group with their open foam tools. This is actually showing how particles from dental treatment in the face of a patient tend to be expelled and land pretty much, look, on the upper thorax of that patient. And that model there is informed by the particle size distribution shown in the diagram top right hand corner, which is from Hyam's work. So knowing a little bit about the dynamics of the material coming from the patient's mouth due to the equipment being used by the dentist, knowing the mass distribution of the particles, one can sort of infer from those data where the particles are most likely to land. And they're landing because these are large particles and they have significant mass and want to precipitate spontaneously under Stokes. Okay, so in the previous slides we looked at airflow. This slide we're looking at particles, heavy particles moving. And here I've tried to put the three together. So this is the precipitation model. Left, the unmodified grill. Middle, modified grill. The right-hand side, unmodified grill, plus the air scrubber. Okay, and they are the spontaneous precipitation models. Okay, perturbated by airflows from the HVAC and the HVAC plus UVC germicidal device. And at the bottom, we see that green ice cream cone. That's the projection field from the patient. On the right-hand side is the particle distribution. Okay. And this representation here is the flow vectors relating to that those combinations of air changes. And if you look carefully, you'll notice that the precipitations on the patient's chest are different from left to right. So this is a nice example of how we've rejected the idea that air sanitization using air changes is simply good mixing. We require a much more subtle information process applied to the data. We've looked at airflows and we've looked at precipitation models, and we've put the two together. Okay, right. So when is a device good and when is a device not good? Well, 22 months ago, people had heard of ultraviolet light, had heard of HEPA filters, and so many people just wanted to buy them to clean up the air. And literally overnight, hundreds of these devices appeared on Amazon and goodness knows what. There's some good ones and there's shocking ones. So it'd be perfectly reasonable for people to say, well, look on the back, and if it's got a CE mark on it, it must be pretty good and it's safe to buy. It's essentially kite marked, isn't it? It's been verified and validated? Well, yes and no. Well, the CE mark on the left is the one we're familiar with, and there's lots of websites down there telling us all about CE marking. Now, these devices are not necessarily medical devices, but they have to be CE marked for electrical safety and that type of stuff. And it's a bona fide index, a kite mark of confidence that the user can have on a product that they bought does something useful. However, on the left, the moniker there, CE, is very, very slightly different, and it stands for China Export. And we have seen from Asia some shocking devices come onto the market that really are nothing more than the output of snake oil salesmen. And I acknowledge Professor Kath Noakes. I think she was the first one to talk about snake oil and snake oil salesmen. There's a link down here on the slides where I will copy to people. There's the updated version of where we're going with CE marking as we become UK based, having left the EU. This, I thought, is a nice example of just how absurd some of the claims are. So this is a little portable device that you waggle around in front of your disenfranchised and happy baby. And look, I think it might be a bit of an issue getting a true kite mark on that, don't you? Okay, so we moved into, for the Chief Scientific Officer, under a committee working group, under the auspices of IPEM, chaired by Andrew Douglas, the Deputy Chief Scientific Officer. We put a group together to look at all the physics and then tell people whether or not we think these devices are verifiable. So verification, are the physics and engineering per the spec? I'm tempted to say, does it do what it says on the side of the tin? So first thing, pack test. Of course, it needs some sort of electrical test, doesn't it, to show it's sanitary in that regard, and we'll just use the low voltage directive. As clinical engineers, we would like more, but that's the very, very minimum. But these devices are going to say it produces a certain UV irradiance or photon power, and it's going to produce a certain airflow. Well, if you multiply the irradiance by the airflow, you get a dose. So they'll be implying a dose. Okay. Can this dose be measured? If so, dose okay, pack test okay. This is a verifiable device. So we invested in a spectrophotometer working in the far UV, straightforward physics, how to use that. Small hole in the side of the chamber, put in the probe, measure the local irradiance, few measurements, try and infer what the flow field is and the irradiance field is, and come up with an estimate of what the dose is like to be. Okay, and this is the spectrum that we pick up using the spectrophotometer, and that's that one there that I'm pointing to, the largest peak. That's the one we're looking at, because that's 254. Measuring the gas flow, the airflow, simple vein anemometer or a hot film. So you've got the pack test, you've got the irradiance, you've got the flow. That should be enough. I should have been able to go to the world and say, these devices have been verified. We recommend that you can use them. Unfortunately, IPC World, Infection and Effects Control, had absolutely no truck with this at all. How about telling us, does it work? Quite correctly, they actually wanted to know, does it deactivate SARS-CoV-2? Does it kill bacteria? Well, that wouldn't be verification, that would be validation or biovalidation. So this is where our group of critical engineers, physicists and engineers had to go into the new world of microbiology. So we built ourselves a biovalidation environment to answer the question, does it kill bacteria, a particular device? Does it deactivate viruses as per claim? Test regime, take a room, regulate the temperature, regulate the relative humidity. Humidity is quite a strong function of how ultraviolet light deactivates RNA and DNA. Take a test organism. Okay, well, why not take SARS-CoV-2, the virus which causes C19, COVID-19, or maybe use a bacterial surrogate, i.e. a bacterium, which is kind of good enough because it's easier to handle than the virus. Inoculate the room, this large room, with a nebulizer, a Venturi system, ultrasonic, stir it all up with lots of fans, then sample the air as the device runs over an hour to estimate the clearance rate. Sample onto an agar plate so these bugs can be grown, or sample the air into a liquid and then sample the liquid into vials, which then can be looked at by the microbiology lab. What assay can we use? Well, we can use PCR or LAMP for the virus, in theory. If it's a virus, we can challenge bacteria on an agar plate, or if it's a bacterium, we can simply grow it on a plate. So these are the sort of things that we had when we thought, how can we design this experiment? Well, temperature, easy, relative humidity, yeah. Test organism, SARS-CoV-2, there is no way that you can let engineers and physicists start throwing SARS-CoV-2 around the place. So we went for a bacterial surrogate, and we actually chose Micrococcus luteus, and I'll tell you about that in a moment. Inoculation, we used a simple nebulizer, such as used for people in their salbutamol or whatever, for asthma. Sampling, could sample directly onto an agar plate, but we decided to sample into a liquid using a Coriolis system, which I'll demonstrate in a moment. Assay, we're not using a virus, so we're not going to use PCR or LAMP. We're not going to grow bacteria and challenge them with a virus because we're not using a virus. We're simply going to grow our collected samples on an agar plate, and that's going to be done by our colleagues in microbiology. Okay, so we built ourselves a room, and we called a Cat 1 room because you had to be safe but not super safe. And the bacterium that we chose, Micrococcus luteus, is minimally pathogenic. It occurs naturally in the environment. It was one of the first bacteria described by Alexander Fleming. It's on our skin naturally. So with reasonable caution, it can be used in regular laboratories. We found ourselves a 55-meter cubed deserted room in the old medical school, and this was going to be our pseudo environmental chamber. So Micrococcus luteus, a number of reasons why we liked it. It's easy to grow, it's easy to see, it's bright yellow spots, but its UVC behavior is reasonably well understood because the cosmetics industry use it for sun protection factor testing. And there's quite a lot of literature on that. Not good literature, but there is some amount of literature on that. The test conditions, 25 Celsius to 45% relative humidity, and air mixing. We asked Fred for a CFD description, and he just said, just make it gusty. So we use 4 oscillating room fans. So quickly on the left-hand side, this is what few colonies of Micrococcus luteus look like when they grow on a plate. We're not going to use a plate like that. I'll describe that in a minute. There's the nebulizer, the inoculating device, the bottom left-hand corner, throwing it into the room. And there is the inoculating nozzle in front of an oscillating fan. So that's throwing the challenge, the inoculum, into the air. And then we now sample that air as one of these air cleaners in the background here is running. These are germicide and UVC cleaners, 2 on test here. We sample the air at 10-minute intervals into a liquid. On the left is a very fancy, very expensive machine that does that, which broke on day 1. So being engineers, we built our own. So there's a suction fan here, a curly pipe, and a Coriolis sampling head here. And at the bottom of that is a vessel which has got some receiving liquid in it. And under the table, there is a low pressure line going to a vacuum pump. And this now should demonstrate the Coriolis sampling going on. So one of the devices being run in the background, and every 10 minutes we're turning on the machine and sampling air. There we go, sampling air into 10 ml of buffer. Okay, now that might seem reasonably sophisticated, but I'll introduce you to our engineering solution of how we produce the vacuum. That's what you call an engineering solution, I think. Anyway, so that's a DIY Coriolis Dyson type impingement. So those samples then go to a microbiology lab, and there each one is plated onto agar. Now they do that using a spiral plater. Now this is a demonstration of a spiral plater, not inoculating the agar with our test liquid, with ink, just to demonstrate what's going on. So the sample is laid down on the agar at changing radius at constant velocity. So across that agar plate now are concentric rings of different concentrations of what will be our inoculated, captivated Coriolis sample. And we generate 10 of those. Beg your pardon, we generate 7 of those per hour, i.e. 1 every 10 minutes. Okay, these are then grown overnight and read in a digital reader. Okay, and that's pretty much what a plate looks like when it's been grown for 48 hours. The microbiologists count those for us and tell us what the potency is, the patency is of that recovery, i.e. the concentration of bugs that were in the air at the time that we sampled it. Okay, and we can reduce those data into log reduction curves. And a log reduction curve of an exponential process, of course, is a straight line. A lot of data goes into extracting this information. Microbiology, please forgive me, my colleagues in the microbiology lab, is at best semi-quantitative. There are lots of random errors in there that you can't control. So the only way to reduce those data errors is to oversample, take lots of readings and do averages. So a single run on the device for a given flow rate requires us to do 5 hours of recording, 5 separate runs, get the log curves and average the log curves. But an exponential equation, of course, is dictated by one parameter, really, from normalized starting concentration, and that's the time constant, which is the rate of display. So the dynamics of removal of a bacterium from this space by a ultraviolet germicidal sanitizing scrubber is described by a single parameter, and that is related to the time constant of removal. But the metric that we've come up with is for a given machine under a given set of conditions, it is the time to deliver 1 cubic meter of air to 1 log reduction, which is 90%. So it's internally normalizable, and it's independent of the room. And that's the biovalidation index that we feed back to the manufacturer. So to date, we've done about 20 devices. That's 180 runs. That's 180 hours of running. And there must be something like 1,000 agar plates that have been grown up and assayed by our colleagues at Feedwater Laboratories. Okay, just to finish pretty much now, where are the regulation standards that tell us how to use these devices responsibly? Well, unfortunately, there aren't any. HTM 0301, that's a document that says how you should ventilate healthcare spaces. Very, very good. But it doesn't tell us much about how we can use ultraviolet recirculation or whatever. And although it's a recent document and it's very comprehensive, I think we can look forward to a new release sometime soon, which will take into account how we can augment air changes in hospital and healthcare spaces by using germicide, UVC, or maybe HEPA, or maybe HEPA filters, or maybe combinations of both. So with colleague Mike Ralph, who's the fellow of IMechE and is the lead engineer for NHS England and NHSI. He put together a group of authors to write guidelines and standards for the application of UVC devices for air cleaning occupied healthcare spaces. And this is the author list of people who've contributed to it. Well, what a document this turned out to be. You know, you've got 13 people, you've got 13 opinions, haven't you? It's very difficult to put this together. But just before Christmas, we got this paper together. It's about 28 pages, I think. And it went to Cabinet Office, and Cabinet Office is now going to sub-edit it eventually. It'll come back to us, and we hope we can refashion it and make it into a British standard. So it's the start of kite marking. Now, I don't expect you to read this. This was a 4-page document that we developed in Liverpool, and it describes in exact detail the biovalidation program of how we use our environmental chamber, how we use Micrococcus luteus, what inferences we draw from the implications in the data. And this is just the first page. This document is now going to be owned by NHS supply chain. And I think where we're going with it is that no company may tender their devices for NHS contracts unless it has been biovalidated by the protocol I've just described, or the manufacturer can evidence that equivalence biovalidation has been performed. And that's pretty much where we are at the moment. I think 6, 7, 8 devices have been along this pipeline now. We have a version specifically for induct, which is on the screen now, and a slightly modified version for the portable devices, which I started talking about earlier on. So from a minefield of snake oil, from a minefield of devices that makes your baby happy and stops it crying in the bath, we're starting to kite mark. We're starting to come up with standards and standards that can be enforced as regulations going on into the future. Okay, so where are we on this journey? Where's the evidence? What have we done here? Well, we've got this end-to-end V&V pipeline now that will inform standards, that will inform regulations. We've got a number of software design tools. We have lots of CFD. The ES group has got DIY models now that will help you design optimum ventilation of healthcare spaces. And we can calculate irradiance, and we've done some work with a company, Midtherm UV. They've been very, very active in modeling irradiances in devices. And I thank Barry for helping with that. And we have a biovalidation methodology now, which we're going to publish, and hopefully that will be adopted by other healthcare providers throughout the world, in fact. And we have a recommendation document that eventually will escape from Cabinet Office and will become useful. I should note that the recommendation document has been sponsored by the IMechE. The big question, I think, that needs to be asked is, yes, Micrococcus luteus is extremely resistant to ultraviolet light. We're using it as a surrogate for all other bacteria and viruses. In a hand-waving, non-scientific way, we're saying at this time that if your germicidal UVC devices will kill Micrococcus luteus, it's a total breeze to deactivate a virus like SARS-CoV-2. We are now working quite hard with the Liverpool Tropical School of Medicine in their CAT3 laboratory with SARS-CoV-2 to see whether that is a true or false premise. Well, that concludes my talk. I hope that has been useful, and I do want to take this opportunity again to acknowledge my colleagues who contributed to my journey on this story. So thank you.
Thanks a lot, Tony, for taking us along your COVID story with plenty of practicality in the middle. I'm sure the audience has appreciated the DIY Henry-based sampler. I'm going to turn to the questions. For those of you who haven't found the question tool, it should be pretty obvious on your screen, and it's the only way to put questions to the speaker. So I'm going to take them in the order they came. There are a few already. The first one is about practical solutions that could be implemented at a large scale in low or middle income countries.
I'm sorry, could you just repeat the last bit there, Sylvan? Sorry.
What solutions would you say are suitable for large-scale deployment in low and middle-income country? In other words, are those scrubbers cheap enough for broad adoption?
Yeah, well, two things there. Large spaces. Well, I think the whole future of where we are living with COVID, just to be specific about the response to the pandemic at the moment, it's going to be piggybacked on the back of the carbon agenda, the new ways of ventilating buildings, in-duct treatment, augmenting big HVAC systems. It's not an expensive thing to do. It's very, very, very scalable. However, the portable devices that I've shown today, I think the biggest one we've looked at is 750 cubic meters per hour. So a number of those, say 4 of those would ventilate de novo quite a large ward. So that's quite a scalable thing, and that is quite an economical way of bringing a good air sanitization to areas for minimal cost.
Thank you. The next question is about humidity. You mentioned in one of your slides, humidity was a key factor.
Yeah.
Can you give us a little bit more on, what range of humidity is it practical to keep for those scrubbers to work?
All right. Well, the ranges of humidity are a real challenge for us in our environmental laboratory, because how do you control humidity normally in a room? Well, you turn on the air conditioning. That's the last thing you can do is you're actually testing something to augment non-air conditioning. So we regulate the local humidity there with an atomizer. There's a whole range of humidities we could have looked at, and we simply chose that, which is pretty much what you might see in a regular healthcare space throughout the year. Okay, but there's no big science to say that the testing at one RH is any better than testing at another RH. However, we do know that RH has got a profound effect as a temperature on biocidal and viral inactivation activity. So we chose an engineering solution, which is one that we could achieve efficiently in our test environment.
Thanks. And do you know if there is a upper limit or a lower limit? Which way does it work? Is humid better for those scrubbers or dry air better?
It goes both. It goes both ways. You can say that it's pretty much a sweet spot where we are at 25 Celsius.
Thanks. Next question. I'm discovering it, so apologies for the small pause. Do you think studies with clinical endpoints and cost effectiveness will be needed, or will the new standards be enough?
No. Longer term, we are definitely going to need clinical FC studies. I just mentioned the one that Frank Mills led in the Maidstone Hospital. I showed that device in the ceiling. That's early days, but they've done a clinical study there. Very, very effective, looking at general deactivation of spores and general microbiological flora in the air. That was a good start. Addenbrooke's have done some very good work actually using smart sampling and PCR, I think possibly LAMP of SARS-CoV-2, COVID-19 in clinical environments, and that's just been published. But we're going to need a whole new history, I think, to put together of clinical effectiveness. That we know that some longer term studies are being done at schools at the moment, and there's quite a few also being done in clinical environments. But absolutely essential. The IPC community are just about okay with what we're doing in terms of biovalidation at the moment, but their ideas really are focused on long-term healthcare benefits from establishing clinical scenario.
Thanks. The next question is taking us outside the hospital. How applicable is this UVC approach to, say, cruise ships and other non-healthcare settings?
Entirely so. I've seen it in buses. I've seen it in bus shelters in Korea. I've seen it in factories. I've seen it in offices. I think the potential is there, And I think academic proponents of this type of technology include Kath Noakes at Leeds, and I know that she's done a lot of work in the potential of UVC in a number of ways of being used in the built environment. I think that we've all got very excited about this in the last 24 months because we've been so focused on the pandemic. And it's quite recent, really, that we realised that the longer term, our trajectory is going to be the carbon. I think the carbon program. That's where I think it'll be, and the IPC benefits will come for free, if you like.
Thanks. The next question goes back a little bit on the first one, but I think there's clearly a concern of how affordable are those technologies for the countries who really don't have much means, where, well, healthcare rooms are not air conditioned other than opening the window and the likes.
Yeah. Well, there's a whole thing, isn't it, about you want a ventilator room, you open the window. Well, in real terms, you can't help but be distressed by the number of hospitals you go to where the windows are painted closed. You go to schools, the windows are painted closed. You go to some examination rooms. In my own hospital in Liverpool, we have rooms with no windows whatsoever, no ventilation at all. HTMO3 would not allow us to build hospitals like that now, but it's not retrospectively active. So we build a new hospital tomorrow. HTMO3 will advise us strongly on what ventilation rates we're meant to have. But so many of the healthcare spaces that we have to deal with in the UK at the moment have got virtually zero. So the quick fix mitigation are these devices. And somewhat distressingly, I found that just yesterday that the government funding for bringing this technology into care homes has finished. I think it finished last week or something like that. So we've been doing a lot of work with care homes where there's been outbreaks, and we're delivering the devices and designing sanitation systems, to protect these old and fragile and vulnerable people. And the uptake has been very good of equipment, but that's in part because there was very good funding. That funding is now gone. So I think I've been quite cavalier in saying, "Oh, this is cheap technology." Cheap. It's always cheap if it's free, isn't it? Or it's reasonably cheap if it's subsidized. That's gonna change. It has changed now. And just a system that I recently designed with colleagues. It was a great fix. It would have done the job within 12 hours. The system would have been active. The care home could no longer afford it because they lost their finances.
Fantastic, Tony. This brings us to time. Our speaker generously said he will follow up on requests for further information through emails. You will get Tony's email address in our thank you pack, together with a link to the recording of this talk in a few days. So it remains for me to thank you again, Tony, for taking us along your journey and being available for us today.
Okay.
Thank you and goodbye.
Thank you, everybody. Goodbye.